Okay, so in this video we're going to be looking at bearings and triangulation. I would say that bearings is certainly the hardest part of the trigonometry section of the geometry and measurement, and certainly one of the harder parts of the geometry and measurement. It's really important that you read questions involving bearings carefully, and we'll talk about that here. So bearings indicate the direction of one object from another. Okay, and we will work with true bearings, which are also called three-figure bearings. And when we have a true bearing, we always measure the bearing relative to north. Okay, so sometimes we see like compass bearings where, you know, this is north and this is east and this is south and this is west, and if that angle there is 20 degrees, we might describe that as, actually, sorry, I've done that interestingly, so that would make that 70 degrees, and we always go north-south first, south 70 degrees east, and we would describe it as a compass bearing. So we know that it's somewhere between south and east, and from south to east 70 degrees. We're not using compass bearings here, we're using true bearings, which are always measured relative to north. Okay, so therefore if we had this 20-degree angle here, measuring that as a bearing relative to north, sorry, that should be an N, the bearing would be 90 plus 20, so 110 degrees, and we sometimes write a T after it to say true. It's conventional to write a true bearing using 3 digits, so if it doesn't have 3 digits, so let's say it was here and that was 30 degrees, we would write that bearing as 030 degrees true, although to be honest that's becoming a bit less common. I wouldn't be too worried about that. And it's also conventional to sometimes use the letter T after it to indicate that it's a true bearing. Again, you know, that's probably not that conventional these days, or not necessary anyway, but that's what it means if you see it. Okay, so in the diagram we've got here, we've got north measured vertically up, and we would always draw our diagrams with north measured up. And then we can see here that the bearing from O to A is 70 degrees. So what it means, the key thing here is the word from. It's really important that you're clear about where you're measuring your bearing from. So if we're measuring our bearing from O, that means we're standing at O, facing north at O, and turning in a clockwise direction. So that is the bearing from O to A, and it is 70 degrees. Okay. We can also see the bearing from O to B is 110 degrees. So from O is what's important there. I'm standing at O, so from O. I'm standing at O, I'm facing north at O, and I'm turning clockwise until I'm facing the direction of B, and that's through an angle of 110 degrees. So then, what is the bearing from A to O? Okay, so this is where, this time, it is from A. So I am standing at A, and I am facing north at A, and I'm going to turn clockwise because we always measure true bearings in a clockwise direction from north. I'm going to turn clockwise until I am facing O. So I'm going to need to measure all the way around here. That is the bearing from A to O. Bearing from A to O. Now to be clear, the sentence could also say, find the bearing of O from A. But it's still from A. That's where you're standing and facing north and turning clockwise from there. Okay, so if we want to find that angle around there, there's a couple of different ways we can do it, and it all involves our angle properties that we looked at right back at the start of this topic. Now, you could think about it this way. You could extend this line out here. That is corresponding to 70, so that's 70 there, and then adding 180 onto it. 180 plus 70 is 250. We could do it that way. The other way that we could do it is recognizing that this angle and this angle are co-interior, because these are parallel lines. They both go north. So we know co-interior angles, when we have parallel lines, add to 180, which tells us that that's 110. And then if we take away 110 from 360, we get 250 as well. Okay, so a couple of ways to do it, but the bearing from A to O, or of O from A, just the same thing, is 250 degrees true. So it's really important to be clear about where are you measuring your bearing from. And you need to imagine yourself standing at that point facing north and turning clockwise. Alright, example 1. A ship leaves port and sails for 70 kilometres on a bearing of 283 degrees true. Then for 20 kilometres on a bearing of 24 degrees. How far north is the ship from the port? Give your answer correct to the nearest kilometre. Okay, so it's important to have a vague idea of what direction you're heading in with various bearings. So north is obviously a bearing of 0 degrees, or we could talk about 360 degrees. East is a bearing of 90 degrees. South is a bearing of 180 degrees. Okay, that's 180 degrees. West is a bearing of 270 degrees. So if you've got a bearing of 283, that's heading out that way. Okay, and then a bearing of 24, well, that's going that way. So we're going to go out this way for a bit and then this way for a bit. So get that sense of what's happening. All right, so we leave port. Let's put port over here, given the direction we have to go. Port. Okay, if that's horizontal there, we're going sort of out this way for 70 kilometres. Okay, so that's north. That angle all the way around there is 283 degrees. And we do that for 70. Then from this point, so now facing north from here, and then turning clockwise by 24 degrees. Okay, so this is 24 degrees, and we do that for 20 kilometres. Okay, so we want to know how far north is the ship from the port. Okay, so that is essentially, if we start here and finish here, what is the vertical distance between those two places? That's how far north we've travelled. Okay, yes, we've also travelled west, but the question isn't about that, it's how far north. So it's not asking for the direct distance, it's how far north am I, okay? If I'm on this line of latitude compared to this line of latitude, how far north is that from there? Okay, so I'm going to need a vertical distance. So I'm going to make two triangles. I can use this triangle here. I can find that distance. And then I can make this triangle down here to find that distance. And then that total distance is what I want. Okay. Alright, so in the blue triangle, we've got the 24 degrees. We're trying to find x, which is the adjacent side. We have 20, which is the hypotenuse. Adjacent and hypotenuse means cosine. Right-angled triangles, so we can use SOHCAHTOA. So cos of 24 degrees is adjacent, which is x, over hypotenuse, which is 20. And so therefore x equals 20 times cos of 24 degrees, which is approximately 20 times cos of 24, 18.27. Let's just stick with some decimal places. We want nearest kilometre in the end, but we'll get our different values, add them together and just round off at the end. So that is 18.27 kilometres. In the purple triangle, okay, we're trying to find y, which is now we know this angle in here because we know it's 270 to get round to this horizontal line, and 83 is another 13 degrees past there, so that's 13 degrees in there. So relative to that 13 degrees, y is the opposite side and 70 is the hypotenuse, so we're going to need sine. So sine of 13 degrees is the opposite length, which is y over the hypotenuse, which is 70. And so y is 70 plus, 70 times sine of 13 degrees, which is approximately 15.75. Okay, and so therefore our total northerly distance is 18.27 plus 15.75. Let's add those nice exact values together with our CAS. And then once we've done that, round off to the nearest kilometre. So it is approximately 34 kilometres. This doesn't seem far enough to me. Oh yeah. 34 kilometres. Let's just have a think about the reasonableness of our answer before we move on. Let's have a think about that blue triangle, 18.27. Well, we definitely knew that the x has to be less than 20 because 20 is the hypotenuse. So yes, I'm happy with that. And in the purple triangle, well, that 13-degree angle, that's pretty small. And so, therefore, if we think about what that triangle actually looks like, it's quite a long, thin triangle, okay, with only a 13-degree angle in here. So I would expect that to be quite a lot less than 70. So, yeah, I'm okay about that. And then we've got about 16 plus about 18, which is about 34. All right, good. Okay, question 2. Jeff is 20 metres due north of a tree, and Mary is 60 metres due east of the same tree. So due means directly north, okay? So it's not, so up here we worked out that we finished 34 kilometres north of where we started, but it wasn't due north. We didn't finish above where we started, okay? Whereas due north means directly north. They're going to be, if one of them's, if the tree is here, then Jeff is directly north above the tree. Okay, so Jeff is 20 metres north of the tree. Okay, so let's have the tree here. Jeff is north of it, 20 metres. Mary is east of it. She's further away, 60 metres. Okay, so that's what we've got. North and east, the angle between them is right angled. So again, we can use our right angled trig, which is nice. We want to know what is the bearing to the nearest degree of Mary from Jeff, of Jeff from Mary. Okay, so let's think about, so we know that this is north heading up in this direction. Alright, so first one is of Mary from Jeff. So it's the from Jeff that's important. If I am Jeff and I'm facing north at Jeff and I am turning clockwise, what is the bearing? Okay, so the answer to part A is that angle there. Whereas in part B, we want the bearing of Jeff from Mary. The from is the important bit. From Mary. So if I am Mary, I'm standing here at Mary, I'm facing north at Mary, I'm turning clockwise from north until I get around to the direction of Jeff. That angle is the answer that I want for part B. Okay, we've got a right angled triangle though. We can find the angles in right angled triangles. So if we find this angle up here, we can take it away from 180 to find our answer to part A. So let's calculate that. So relative to that angle, 60 is opposite, 20 is adjacent. So we're going to use tan of theta equals opposite, which is 60, over adjacent, which is 20. So theta is inverse tan of 60 over 20, and yes, you can simplify 60 over 20 to 3 if you want. Inverse tan of 60 over 20, oops, sorry, control enter. So theta is approximately 71 point, now we want our bearings to the nearest degree, so let's just keep this 71.6 degrees. And so if theta is 71.6 degrees, then that angle in there, alpha, is going to be 90 degrees minus theta. And so that is 90 minus 71.6. 90 minus this answer here, that is 18.4. Okay, so then if we think about our bearings, so part A, bearing of Mary from Jeff. Okay, so as we said, that's this purple angle up here, and so we know that's going to be 180 minus theta, which is 180 minus 71.6. 180 minus this answer we worked out up here. Oh, sorry. 180 minus, get there eventually, 180 minus this one here. Control enter, and so that is approximately, to the nearest degree we want our answers, so that is approximately 108 degrees. So 3-figure bearing, true. Okay, then in part B we want bearing of Jeff from Mary, so that's the orange angle. And so we've worked out alpha, and so we know that that whole orange angle will be 270. It's going to be 270 around to there, plus alpha. So it's 270 plus alpha, which is 270 plus that 18.4, and so 270 plus this to the nearest degree is 288 degrees true. So it's really important that you're clear about which angle you are finding. Where are you measuring the bearing from? Stand there, draw in the north line, turn clockwise until you get around to where you want. Okay, question 3. Two hikers, Alphonse and Bernard, start at the same position. Alphonse sets off from this position on a bearing of 20 degrees. Bernard sets off on a bearing of 15, sorry. Okay, so if they start from here, 20 sort of that way, 315 sort of that way. Okay, so that's what's happening. After walking a distance of 300 meters, Bernard realizes, so Bernard's on the 315 degrees, so he's gone 300 meters. He realizes he can see Alphonse at a bearing of 100 degrees. Okay, so once he's gone 300 meters, so Alphonse is heading off on this direction. Okay, that's 20. Bernard's gone this way, which is 315. Okay, so I'm just drawing a rough sketch and then I'll tidy it up. So Bernard's here, he's travelled 300 meters. He now realizes that he can see Alphonse at a bearing of 100 degrees. So from where he is now, from where Bernard is, he can see Alphonse at a bearing of 100 degrees. So if he faces north and turns clockwise by 100 degrees, which is a bit more than 90, then that's where Alphonse is. Okay, and so we don't know how far Alphonse walked. We have that bearing instead. We've got this 300 here. We can work out if there's 20 degrees here, if that's 315, it's another 45 to get to 360. So we can work out that there's a total angle in there of 65 degrees. And then we should be able to think about using, we haven't got a right angle triangle, so think about using our sine rule or cosine rule. I'm just going to tidy that diagram up slightly. Oh, that's probably okay. I think we can go from there. Alright, so what do we know? If we think about that red triangle, we now know that that angle in there is 65 degrees and that length there is 300 meters. And what do we want to know? How far apart are they at this moment? So this is the length that we want. Okay, we haven't quite got enough information here, so let's think about some other angles. Let's think about what we know about using this 100. We haven't really used that. So if we think about what's going on up here, okay, that's 100. Now, we know, let me get a different colour so you can see what I'm talking about. That angle there is 45 degrees, okay, and that angle there is a Z angle, it's an alternate angle, that is also 45 degrees in there. So that means we can work out that if there's 145 degrees, the remaining 35 degrees to get to 180 must be in there. Okay, so then once we've worked out that angle, we could also work out this angle over here on the right, just by adding them up to 180. So 65 plus 35 is 100, and so this must be 80 degrees over here. So we've got all the angles. We've got that important information we need for the sine rule, which is a length and an angle opposite each other, and we can work out x. So we're going to use sine rule here. Okay, so we know that x divided by sine of the angle that's opposite it, which is 65 degrees, is equal to 300 divided by sine of the angle opposite it, which is 80 degrees. And then we can do the rearranging. It's a length, so we don't need to use solve to take care of the ambiguous case. So 300 over sine of 80, sorry that's a bit illegible, let's go again, times sine of 65. 300 divided by sine 80, and then times sine 65. Control enter. And so that is approximately 200, what do we want? Nearest meter, 276, and it's meters is the distance between them after Bernard has walked for 300 metres. Okay, triangulation is when we might not be able to measure certain distances, but we can measure other distances and lengths and then use trigonometry calculations to find the distances that it's impossible geographically for us to measure. Obviously, these days with GPS and satellites and things, it's not ever impossible to measure a distance. But hey, not every average Joe has access to, satellites, although GPS and Google Maps, I get that. Having said that, those things work because, of various trigonometric calculations that are going on. Okay, so, as I said, sometimes certain geographical or topographical features make it difficult to obtain measurements. In these situations, surveyors use triangulation to calculate the required measurements. Often bearings from two locations are used to precisely position a third location. So triangulation is used when either the distance between the two locations, when the distance between the two locations is given and the direction from each of these locations to the third inaccessible location is given. So if we know the distance between A and B, and we can work out what the angle or what the bearing is from A to C and the bearing from A to B, then we can work out these two angles, and we've got a known distance and two angles and a triangle, and we've got enough information to find what we need. Okay, let's have a look at an example of this. So two fire spotting towers are 7 kilometres apart on an east-west line. Okay, so east-west, two fire spotting towers, Tower A and Tower B. Well, actually, we're not sure which one's which. For now, Tower A and Tower B, they are 7 kilometres apart. From Tower A, a fire is seen on a bearing of 310 degrees. Okay, so let's have a think about that. So 310 degrees is sort of out that way. Okay, so that's from Tower A. Whereas from Tower B, the same fire, so if this is B, the same fire is at 20 degrees. So if those angles are going to meet in some way, this can't be B. If we made this B and this A, then that's a bearing of 20 degrees out that way, and that's a bearing of 300. The fire, we're not talking about the same fire, okay? So it's the same fire they're seeing, and so therefore, this has to be B, and this has to be A, okay? So from B, we're looking at a bearing of 20 degrees, okay? So it's heading out that way. And from A, we're looking at a bearing of 310 degrees. Now, 310 is 40 degrees more than 270, so I'm sort of thinking about that when I'm drawing it. Okay, that angle all the way around there is 310. If this is 20 degrees here, that's 70 degrees there. Okay, and so this is where our fire is. Okay, so we want to know which tower is closer to the fire and how far is that tower from the fire. Okay, so we can see from having drawn a vaguely accurate diagram that this 20 degree bearing here is going to mean that that tower is closer to the fire. Okay, so we can see that Tower B is closer to the fire. Okay, so this angle out here is 50 degrees, so that's going to have to be a longer distance. This is if we think about the angles in the triangle. This angle is smaller than this angle, okay? So therefore, this produces a shorter distance than what this does. If you open out to an angle of 70 degrees, that distance is inherently going to be bigger than if you open out only to an angle of 40 degrees, okay? Smaller, bigger. So it's important to understand that, if you're talking about triangles, the smallest side length of a triangle is going to be opposite the smallest angle. So if that's the smallest angle, that's the smallest length. If that's the biggest angle, that's the biggest length. Okay, so the angles are defining, how long the side length opposite them is. Okay, so Tower B is close to the fire. So which tower is closest to the fire? And how far is that tower from the fire? Okay, so we want to find that distance. We've got a triangle. We've got two angles in that triangle. We've also got the length of 7. Okay, so we should have enough information here. let's think about whether we use sine rule or cosine rule. So we don't have that important actually we do, because we could calculate this angle. 70 and 40 is 110, so that leaves 70 degrees up there. So we've got that combination that would allow us to use the sine rule. So we could, and then we want to find x, so we use that combination. So we could definitely use the sine rule. We could also, I think, have used the cosine rule without working out that 70. But it would have been a bit more complicated. The sine rule is always a bit easier. If you can use the sine rule, I would choose the sine rule over the cosine rule. Okay, so therefore, if we use sine rule, x over sine of 40 degrees is equal to 7 over sine of 70 degrees. 70 degrees, not 700. And so x is going to be 7 over sine of 70 times sine of 40. 7 divided by sine 70 times sine 40. Control enter. And so x is 4 point, what accuracy would we want? 1 decimal place, 4.8 kilometres. Okay, you could also work out y and show that that's a longer length, but you shouldn't need to work out both distances to know which one is the shorter one. The one opposite the shorter of those angles will be the shorter length. Actually, interestingly, now that we've worked out all the angles, we have an isosceles triangle here. So the minute that we knew that this angle up here was 70, it's the same as this. And so that automatically tells us that these two lengths are the same. And so this is also 7 up here. So that could have been useful as well. It meant if it's isosceles, we could also have thought about splitting it in half and using right-angled triangles. Okay, so lots of different ways you can go about doing it, and that will always be the case in these kind of problems. You can create right-angled triangles, non-right, and use SOHCAHTOA, non-right-angled triangles, and use sine rule or cosine rule. Sometimes it's a choice between whether you use sine rule or cosine rule. So it's about being flexible and trying to use the most efficient method. Okay, so there is some work here both in exercise 18E and then some further examples involving bearings in Appendix E of your booklet.